In this video, we'll provide, for the first time, concrete evidence that the lazy union approach to the union find data structure is viable. Specifically, we'll prove that the worst case running time of both the find and the union operation is logarithmic in n, the number of objects stored in the data structure. We're going to do even better later once we introduce a second optimization known as path compression, but an important stepping stone is to understand why just union by rank already gets us to a reasonable logarithmic runtime bound. So a quick review of the lazy union approach to implementing the union find data structure. So with each node, we're going to maintain a parent pointer, and it's no longer the case that we insist that the parent pointer point directly to the leader of a group. Rather, we just insist that the collection of parent pointers induces a collection of directed trees. The root of each tree, that is the node which is its own parent, we're going to define as the leader of that group. So given any old object x, how do you implement find? How do you figure out what the leader vertex is? Well, you just traverse parent pointers up until you get to the root of that particular group. So for this implementation of the find operation, the worst case running time is just going to be the longest path of parent pointers that you ever have to traverse to get from an object to some root. So the way we're going to quantify that is using these ranks. So this is again a field that we maintain for each object. And for now, this will break down later, but for now, before we have path compression, we're going to maintain the invariant that the rank of an object x is exactly the largest number of pointers you have to traverse from some leaf to get to x. As a consequence, the biggest rank of any object is the longest path from any leaf to any root, and that's going to be an upper bound on the worst case running time of the find operation. So let's move on to the union operation. So here, given two objects x and y, you need to fuse their two trees, their two groups. So you find the roots of the two trees. So you call a find on x, you call a find on y. That gives you their two respective roots. And now you install one as a new child of the other. And we saw in a quiz in the last video that if you're not careful about which root you install as a child under the other, you can wind up with these long chains and be stuck with a linear worst case time for both find and union. So instead we have this union by rank optimization, which says, well, we want to keep our trees from getting scraggly, and the way we're going to do that is when we have a shallow tree and a deep tree, we make the shallow tree a child under the root of the deep one. That prevents the tree from getting even deeper. Now there is a situation where the two trees have exactly the same depth, that is where the two roots have exactly the same rank. In that case, we just proceed arbitrarily. Now when we merge two trees that both had a common rank r, it's important that in the new tree the rank has gone up to r plus 1. So we need to update, we need to increment the rank of the new root to reflect that increase. So that's where we've already been. Where are we going to next? Well, the plan for this video is to show that with the union by rank optimization, the maximum rank of any node is always bounded above by log base 2 of n, where n is the number of objects in the data structure. Now we just said the worst case running time of find is governed by the maximum rank. So logarithmic maximum rank means logarithmic running time of find. That also carries over to the union operation. Remember, union is just two finds plus constant work to rewire one pointer. So that's going to give us a logarithmic time bound on both operations. So let's see why that's true. So let's begin the analysis with a few simple but useful properties that follow immediately from our invariant, from the way that we change the ranks of objects as we do finds and as we do unions. So the first simple property is focus on your favorite object x and watch this object's rank change over the course of the data structure as we do finds and unions. How can it change? Well, when we do a find, we don't change anything. All the ranks stay the same. When we do a union, all the ranks stay the same. Well, except there is one case in the union where the rank of a single node gets bumped up by 1, gets increased. So ranks only go up over time for all of the objects. That's property 1. So the second property is again pretty much trivial, but really, really useful. So what is the situation in which somebody's rank gets bumped up by 1? Well, it's only take the union of two trees that have a common rank, and then whichever of the two roots that we pick to be the root of the new bigger tree, that's the object whose rank gets bumped up by 1. It's the new root of this fused tree. So in particular, the only type of object that can ever get a rank increase is a root. If you're not a root, your rank will not go up. Furthermore, once you're not a root in this data structure, you will never be a root again in the future. There is no process by which you shed your parent. Once you have a parent other than yourself, you will always have exactly that parent. Putting those two observations together, we find that as soon as an object X becomes a non-root, as soon as it has a parent other than itself, its rank is frozen for the rest of time, forevermore. The third and final simple property follows from a formula we mentioned in the last video about computing ranks. So remember, the rank of a node in general is going to be one more than the maximum rank of any of its children. So if you have a child and there's some path from a leaf to that child that takes 5 hops, the path to you from that child is actually going to take 6 hops. As a consequence, as you go from the leaf up to the root, you will see a strictly increasing sequence of ranks. The rank of a parent is always strictly more than the rank of all of its children. So that's it for the immediate properties. Let's go to a property which is a little less immediate. But still, this next lemma, which I'm going to call the rank lemma, it's the best kind of lemma. So on the one hand, it's just not that hard to prove. I'll give you a full proof in the following 2 slides. On the other hand, it's really powerful. It's going to play a crucial role in the analysis we're doing right now, a logarithmic runtime bound with the union by rank optimization. And we'll keep using it again as a workhorse once we introduce path compression and prove better bounds on the operations. So what's the rank lemma say? Well, it controls the population size of objects that have a given rank. So we wanted to apply at all intermediate stages of our data structure. So we're going to consider an arbitrary sequence of unions. You can throw in some finds as well. I don't care. Finds don't change the data structure, so they're totally irrelevant. So think about a sequence of unions, a sequence of mergers. The claim is for every non-negative integer r, the number of objects that have rank exactly r at this time is at most n, the total number of objects divided by 2 to the r. So for example, if r equals 0, it says at most n objects have rank 0. So that's a trivial statement. There's only n objects. But at any given time, the number of objects that have rank 1 is at most n over 2. The number of objects that have rank 2 is at most n over 4, and so on. And if you think about it, if we succeed in proving the rank lemma, we're pretty much done showing the efficacy of the union by rank optimization. So in particular, once you take r in this key lemma to be log base 2 of n, it says that there's at most one object that has rank log base 2 of n. And there can't be any objects that have rank strictly larger. That is, this lemma implies that the maximum rank at all times is bounded above by log base 2 of n. And remember, the maximum rank is the longest path of pointers traversals you ever need to get from a leaf to a root, and that means the most amount of work we'll ever do in a find, and therefore in a union, is big O of log n. Okay, so I've now teased you with the consequences of the rank lemma, assuming that it's true, but why is it true? Let's turn to the proof. I'm going to break the proof down into 2 claims, claim 1 and claim 2. We'll see that the 2 claims easily imply the rank lemma. So claim 1 asks you to consider 2 objects x and y that have exactly the same rank r. And the claim asserts that these subtrees of these 2 objects have to be disjoint. They have no objects in common. And here by the subtree of an object, I just mean the other objects that can reach this one by following a sequence of parent pointers. So that is, the subtree at x is the objects from which you can reach x. The subtree at y is the objects from which you can reach y. The second claim is that if you look at any object that has rank r and you look at its subtree, that is, if you look at the number of objects that can reach this object x by following pointers, there have to be a lot of them. There have to be at least 2 raised to that object's rank r objects in its subtree. Notice that if we prove claim 1 and claim 2, then the rank lemma follows easily. Why? Well, fix a value for r. 2, 10, I don't care what. Look at all the nodes that have this rank r. By claim 2, each of them has at least 2 to the r objects that can reach them, and by claim 1, these have to be disjoint sets of objects. Well, there's only n objects to go around, and if each of these disjoint sets has at least 2 to the r of them, there can be at most n over 2 to the r such groups. That is, at most n over 2 to the r nodes, objects, with this rank r. So we've reduced the proof of the rank lemma to proving claims 1 and 2. I will do them in turn. So for claim 1, let me go via the contrapositive. That is, I will assume that the conclusion is false, and I will show that the hypothesis must then also be false. So let's assume that we have two objects x and y and their subtrees are not disjoint. That is, there exists an object z from which you can reach x, and from the same object z you can also reach y via a sequence of parent pointers. Well, now let's use the fact that we're dealing with a directed tree, right? So if you start at an object z, there's only a unique parent pointer to follow each time. So that is, all of the objects reachable from z, they form a directed path leading up to the root of z's group. So the only way for both x and y to be reachable from z, they have to both be on this path. If they're both on this path, then one has to be an ancestor of the other. So now we're going to use the third of our simple properties that we observed, that is, on every path to the root, ranks strictly go up each time. So whichever of x or y is an ancestor of the other, that has strictly higher rank. Therefore, x and y do not have the same rank. That completes the proof of claim 1. So let's move on to claim 2. Remember, claim 2 asserts that an object of rank R necessarily has 2 to the R objects or more in its subtree. That's how many objects can actually reach this object X by following parent pointers. So for this proof, we're going to proceed by induction on the number of operations. And again, remember, find operations have no effect on the data structure, so we can ignore them. So it's just by induction on the number of union operations that happen. So for the base case, before we've done any unions whatsoever, we're doing just fine. Every object has a rank of 0, and the subtree size of every object is equal to 1, that object itself, also known as 2 to the 0. Now for the inductive step, there's an easy case and a hard case. The easy case is where nobody's rank changes, where we do a union and everybody's rank stays exactly the same. In this case, we're golden. Why? Well, when you do a union, subtree sizes only go up. There's only more pointers, so there's only more objects that can reach any given other object. So subtree sizes go up, ranks stay the same. If we had this inequality of subtree sizes being at least 2 to the R before, we have it equally well now. So the interesting case is when somebody's rank actually changes. How can that happen? Well, it happens in only one particular way that we understand well. We're looking at a union operation between objects x and y. Suppose the roots of these objects are s1 and s2 respectively. It's only when these two roots have the same rank, let's call that common rank R, that somebody's rank gets changed. In particular, we're going to break ties as we did in the previous video. S2 will be the root of the fused tree. S1 will become a child of it. And in that case, S2's rank gets bumped up by 1. It goes from R to R plus 1. Now notice, in this case, we do have something to prove. What are we trying to establish? We're trying to establish that every subtree size is big as a function of the rank. So S2's rank has gone up, and therefore the lower bound, the bar that we have to meet for the subtree size, has also gone up. It's doubled. So in this case, we actually have to scrutinize S2's new subtree. So what is its new subtree? Well, it's really just composed from its old subtree, and it inherits S1 and all of its subtrees. Well, in that case, we know that S2's new subtree size, the number of objects that can reach it, is just its old subtree size plus the old subtree size of S1. But then we're in good shape because we have the inductive hypothesis to rescue us. So remember, before this union, by the inductive hypothesis, for every object with a given rank, say R, it had at least 2 to the R objects in its subtree. So S1 and S2 both had rank R before this union. So before this union, both of their subtree sizes were at least 2 to the R. So S2's new subtree size is bounded below by 2 to the R plus 2 to the R, a quantity also known as 2 raised to the R plus 1. Quite conveniently, R plus 1 is S2's new rank. So even with S2's new bigger rank, its subtree size is still meeting the lower bound, meeting the target of 2 raised to that new rank, 2 raised to the R plus 1. So that completes the inductive step. Therefore, it completes the proof of claim 2, that objects of rank R have subtree sizes at least 2 to the R. Therefore, it completes the proof of the rank lemma, that for every rank R, there's a most n over 2 to the R nodes of rank R. And remember, the rank lemma implies that the maximum rank at all times is bounded by log base 2 of n, as long as you're using union by rank. And that implies that with this first optimization, the worst case running time of union and find are both big O of log n, where n is the number of objects in the data structure.